effect, which is its effect at the polish rod in pounds, with the position where it was measured, knowing whether or not it was on the upstroke or the downstroke, using the structural unbalance of the unit, and you can calculate your moment. And then from your moment, you can use the torque factors of the unit, and you can calculate what's called permissible load diagrams. Some of us in here know what it is, maybe some don't, so I'm going to give a quick explanation. What that does is that gives you two sets of curves, a curve for the upstroke and a curve for the downstroke. And on the upstroke, if your load passes above the allowable load, that means it translates back to your gearbox at that position to being an overloaded state for your gearbox. So that's the point. Now, if your RPM is measured, you can also include inertia calculations, which take into account the inertia of the weights and all the gears inside the gearbox, the crank arms and things like that, to give a more realistic account. But using just the CBE and getting rid of RPM so you don't have inertias gives you a conservative but accurate estimate of your gearbox loading. So here, take this unit. This is a Mark II unit with about, I think it's about 65% fillage. And you look at it straight away, bam, those red lines tell you the loads that are allowable on the upstroke and the loads that are allowable on the downstroke. And these red lines are only have to do with the surface card. So the fact that your pump card is going through it, that's okay. Notice, you're overloaded on the upstroke from about 90 to 110 inches, okay? That's where your overload is occurring. You look down here, you're not even close on the downstroke, so that's telling you since on the upstroke, your rods are going up, you are rod heavy, and you need to adjust your weights. But at the same time, like we said before, this thing is overloaded even more on the downstroke. But this is just a conventional permissible load diagram. So it would actually have 4 different curves, but that can get confusing. So what we do is we give permissible loads for whenever the motor is motoring instead of generating. But so taking into account amps, your torque speed plot, or your torque polish rod position plot, and permissible loads, that can give you a great feel for how your gearbox is being loaded. And let's look at some facts I listed over here. It's also overloaded on the downstroke, but we can't see it. I just explained why. Minimal inertia effects are happening in these curves. These curves are nice. They're not broken apart. And on the next slide, I'll show you what I mean. The motor is only loaded 49.5% mechanically, so that means for this 50-horse motor to be moving this pumping unit, it's not really loaded that much, so it's not going to feel, it's not going to demonstrate a lot of slip. So that's why it's not very forgiving on those permissible loads. So the fact that the weights are coming around with their inertias doesn't have as much of an effect on this lightly loaded NEMA D. But the bottom line is the gearbox is overloaded. Okay. Now, take into account if we decided to use a more heavily loaded ultra-high slip motor, like we talked about in a few slides in the beginning. Ultra-high slip in the lowest torque mode gives you a more forgiving and more realistic permissible load plot. Look at the bottom there. It's like these permissible loads are riding the peaks. Right here, look at even right there, you can see that permissible load is riding that peak. Why is that? Just like when you're in your car, when you slam the brakes on, we all go forward, right? Well, on a pumping unit, if the weights are coming down, and the rod string incurs a heavy load, the motor goes like that, and the motor slows down because it's trying to move the load, but those weights are coming. 4 or 5 tons of weights and crank arms are coming around, and they help the gearbox and take loads off of the gearbox so that, in this case right here, instead of that permissible load diagram going through that lower peak, the inertia is taken into account, and it actually says even though it would go through a conventional permissible load diagram, the real effects of the inertias of the weights actually make it okay in this instance for the gearbox. So it's not overloaded. In fact, in this case, the gearbox is only loaded 81%. If I were to take this same pumping unit with the card that we had on the last screen, and I was to add more counterweight so it wasn't as rod heavy, that gearbox would have been loaded 98% using permissible load diagrams without inertia. But with inertia effects, we're only loaded realistically 81%. So that's some of the good stuff you can have too by measuring RPMs and knowing some information about different moments of inertias of the pumping unit. Okay, so now comes the point, well, this is all pie in the sky, Dakun. You remember you're wearing a suit, so you don't know much. What happens when I'm at my job and we don't have counterweight to put on the dumb thing, or we don't have another unit that we can put out there? Well, The single biggest impact you can have on gearbox loading is stroke length. If you want, stroke it back one if you have the hole available, and usually you can increase the strokes per minute to maintain that production in the second hole. But because of the way torque factors are calculated, they're calculated using dimensions A, R, and C on the pumping unit. A and C are the walking beam. R is your stroke length on the crank arm. And if you reduce R, you reduce your torque factors by whatever percentages R, the reduction is in R. So if R1 is 42 and let's say R1 is 40 and R2 is 35, well, what's the reduction? 5 out of 40 is what? What is it? What's the percentage? Crap. But see what I'm saying? Okay, so a more expensive solution is taking that pump out and putting a smaller one in there. You going to do that? Probably not these days. Maybe a year ago. Finally, balance it and run it. I mean, if that's what you have to do, that's what you got to do, you know. Put some holy water on it, move the weights, and just move on to the next well. Maybe it'll hold, maybe it won't. But if the economics don't justify changing around equipment or things like that, put it in the best situation that it can be in, and then just stick your head in the sand. All right. Gearbox life, of course, is going to be shortened, but this is not always negative if your production increase outweighs that cost of failure. Okay, good. So we've talked about gearbox. I think we've exhausted it. From that gearbox, we talked about structure, we talked about motor. Let's go now to the rods. Okay. Russell, you had mentioned not understanding this diagram, so I'm going to go